Alright, we're good to go here. Let's see, message. When using valgrind, I keep getting a lot of memory not being freed. So, when you run valgrind, there's a number of things that can happen. The main thing we use valgrind for is to detect memory leaks. So when your program exits, if there's memory that's been allocated but not freed, valgrind will let you know that. But valgrind also pays attention to what you do with dynamic memory while your program is running. And one thing it will catch and complain about is if you, for example, check the value of a field to see if it's equal to null, and you've never assigned a value to that field, right? So uninitialized things are an issue in programs, and a lot of times we don't bother to initialize things because we just forget, and they turn out to be equal to 0, and we wanted them initialized to 0. We didn't initialize them, but the code still worked because, you know, they were equal to 0 by default. But it's still an error, and valgrind will report that to you. And so if your program is not crashing and it's not saying you have memory leaks, but when it's running, before you exit, you're getting messages about uninitialized or conditional jump depends on blah, 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 right? It's usually something like you're checking the sentinel next to see if it's equal to null, and you never initialize sentinel next to null, which is what you have to do when you create an empty linked list. So if you compile with the -g switch, right, do a gcc -g and then run valgrind, it'll give you specific line numbers in specific files where these things are happening, and it's really easy to go in and see what the statement is that it's complaining about. Figuring out what to do about that can be harder, but that should always point you directly to at least where it sees the problem, and then you can work backwards from there. You did not necessarily need to initialize the fields in the sentinel node other than the next field, right? Next has got to be initialized to null, because every time you work with a linked list, you're going to start off with, you know, setting something equal to sentinel next, and if you haven't initialized that to null, it's an uninitialized value. But you shouldn't have to put particular values in the plate first and last name of that node. Although it's nice to do that. It's nice to put something in there that you'll recognize. If you set it to null and you accidentally use those strings, you'll segfault almost certainly. And it's nicer to, you know, sort of have a noticeable value in there, like our magic integer that we put in PA1's linked list. Let's see, but not initializing plate first and last creates these memory leaks. Are they definitely memory leaks, or is it other issues that valgrind is complaining about? Because not initializing shouldn't be a problem, but make sure you don't try to free plate first and last if you haven't allocated memory to them. And if that's not explaining the behavior, I would say try to put together what's called a minimum working example. You know, a set of your code that you can run through that clearly shows this problem, and then come by office hours and screen share, and we can go through the code in that particular case and see exactly what's happening there. And all these problems that, you know, come up when you're working on an assignment, these are little golden nuggets, right? These are the goods. These are the things you want to dig into, because every time that you write code to do X and it does Y instead, right, you have found a huge learning opportunity. There's something that made you write this code that you thought would do this, but it's doing that, right? If you ignore that, there's something that's missing or misconnected in your understanding, and you're not taking the opportunity to find that and correct it, right? So when you find a bug, that's your golden learning opportunity. That's when you want to really, really dig in and start exploring in the debugger and, you know, adding print statements or whatever you like to really, really make sure you understand it, right? Don't just, you know, change it and try to get it to go away, because that's, you know, it's like someone comes up and says, I'm going to tell you the secret of the universe, and you like slam the door at them and run away. You wouldn't do that, right? Well, that's what's happening when you get, you know, a weird bug in your code, especially if it makes no sense. If you're like absolutely sure your code should work and it's not working, that's, you know, the greatest of all possible things that you can learn if you dig into it. If you just, you know, change your code to do something else and your code starts working, well, you don't know what it was that you were doing wrong, and it'll happen again, you know, and maybe it'll happen in a job interview or when you're, you know, delivering code to a client. So don't run away or shy away from those bugs, right? Jump into them. It's how you're going to learn. And the bigger the bug, the better the learning opportunity. All right, so so other questions. I did not. I will for PA4, but that database has 1,000 entries, and so if you wrote your code to only work on that database, you deserve the A. But no, I mean, I look at people's code too. But I did a number of experiments with that database. I did not exercise your main program as thoroughly as I might have in the past and as thoroughly as I will in PA4. But for PA3, I was mostly interested in the hashing part, right? That's the kind of fundamentally new piece to this assignment. And so I wanted to make sure that you were hashing correctly and you understood how the hash function worked and what it was for and so on and so forth. And so I want to go through and make some comments about PA3 and just sort of you know, hit the main things I saw. As usual, most people did really well on this. I tried not to nickel and dime people as much, but there were some sort of conceptual issues that popped up. So I want to go through some of what I saw in PA3 and give you some things to think about and maybe correct. And then I want to talk about PA4, which I posted last night, and will be similar in some ways to PA3, so you get to reuse more of your code from the last assignment for this next one. So I want to go through that, and then I want to come back to talking about trees. And so we're in week 7 right now, and we'll probably spend the rest of the week talking about trees. Up to and probably starting to talk about balancing trees. And then next week, week 8, and it's a short week for the Monday class because Monday's a holiday, so we have only one meeting next week. But I want to start talking about sorting and searching. And we'll go through several types of sort algorithms. And I may change the order of these. And then I want to talk about dynamic programming. I may switch these actually, because I think your last assignment will be on dynamic programming, and I want to talk about tries and do some wrap up and so on. So that's roughly where we're going the rest of the quarter, and then we're done, right? We're in week 7. We've got 4 weeks left in the term. So this has been a fast quarter, faster than fall somehow. So we'll talk about programming assignments today, and we'll continue digging into trees today and probably Wednesday. So if other questions come up, let's talk about those. But until then, let's just talk a little bit about PA3. So I think I have PA3 from everybody who's turning it in. If you had 4 slip days and hadn't used any of them and you're planning to use them, then you still have time to turn in PA4. Let's see. Issues that I saw. Don't let your code seg fault, right? Test your code pretty thoroughly. Seg faults are a big deal breaker in code, right? It means something that the programmer did not anticipate has happened. And that's never something you want, a teacher or a customer to think about your code. So test your code and make sure it does not seg fault. Now you have a total of 4 slip days for the quarter for this course, and you get to use them however you like. All right. So I had some code where if you just hit an empty enter with an empty line, it seg faults, right? Don't do that. If you don't put in a database file name when you run the program, don't seg fault. If you put in an illegal hash table size like -5 or 0, don't seg fault, right? So try all these different bizarre ways of using your program. Imagine you know nothing about the program and just use it and see if you can make it break. So watch out for seg faults. The assignment specified that you should add your new license plate to the beginning of the linked list. Some people added it to the end. Does it work? Sure. But why take the time to move to the end of the linked list if we don't care about the order in which we store things? Now, if we're alphabetizing the list to try to do something fancy, right, we can do that. But if all we want to do is add something to a linked list, put it right in the beginning. Just add it right after the sentinel. And that's the fastest way to add it, and it's also what the assignment said to do. There were a few cases where hitting the enter key just repeats the previous command, and that's definitely not something you want to do unless you're asked to do that, right? That could be a nice feature. GDB does that. If you just hit enter, it repeats the last command. But when you're typing in commands to do searches or going forward to manipulate a data structure, don't just arbitrarily repeat the previous command if the person hits enter. And I saw a lot of different ways that people tried to parse command line arguments, runtime arguments, and this is good. This is stuff to figure out. But we had the following possibilities. We could say star load. We could say star dump. We could say star dump with a number, or we could put in a plate. And when you're trying to decipher user input, so let's say the user has typed in a command and it's sitting in a variable called buffer or whatever, string input. How do we tell which of these situations has occurred? Well, this is the default case. So really you want to see, did they do this, did they do this, did they do this? If it's not one of those three, it's a license plate lookup. And just take your buffer and pass it to hashFind. And these two are very straightforward to detect, right? Just do string compare, buffer, star load, and see if it's equal to 0. Now this is assuming that I've removed the new line at the end. And usually if you're going to do a lot of parsing on input that you're getting from fgets, you need to remember there's a new line at the end when you come back from fgets. It's usually easiest just to chop that off, so you don't have to keep checking for a new line in here and so on. So these are very straightforward. Just do a string compare to load or dump. Anytime you want to parse to see anything involving an integer, think about scanning. Right? So best way to do this, do a scanf on buffer, star dump, %d. And if you want, you can do the extra thing. And make sure it returns a 1. I don't think I did the extra pickup thing in the sample program, so if you didn't do that, that was fine. But use scanf because you're looking for a particular pattern of characters followed by any pattern of characters that represents a legal integer. Right? So, we don't have negatives, but it could be negative, positive, whatever. Use scanf for that. And so this is 3 if statements. If the buffer is star load, call hash load and go back to the top of the loop. If the buffer is star dump, call hash dump all, or make a for loop that dumps each of the cells. If the scanf of this returns a 1, call hash dump with num and go back to the top of the loop. Otherwise, call hashFind with your buffer. Right? So flowcharting can help to sort of, see how I'm going to go through these different possibilities. Or pseudocode or something. But the way you do this can drastically change, how complex your code is. For example, if you start off with this, that's fine, right? Because if this returns a 1, you know it's a dump followed by a number. If it doesn't return 1, it's not a dump followed by a number. But a lot of people tried to do a scanf with a %s and a %d and a %s, and then look at the value that comes back from this, and if it's 1, do this, if it's 2, do that, if it's -1, do this other thing. Some people tried to scan 2 or 3 times with different patterns, and then looked at combinations of the return values from the scan functions. And if that makes sense to you, that's great. But make sure the way that you're writing your code corresponds to how you would do this yourself, because that's usually what makes the most sense to you. So if someone hands you a string and says, hey, process this string for me, well, what would you do? You'd probably check to see which command it is. Is it a load? Is it a dump? Is it an add? And if it's none of those, it's a lookup. So go look through your database, your card catalog of license plates, and try to find that buffer. All right, hash function error. So I gave you an explicit hash function to use, and most people used this. Some people did not. Some people used fairly different hash functions, and it works, but it's not doing what's required. So the hash function you were supposed to use was adding up the square of each character's position times the character, and then reducing by the hash table size. So if plate is an array of characters, this gives you the ASCII code. It's really just plate bracket I, right? I plus 1 times I plus 1. Let's talk about this sum. Let's think about for loop limits. So you're trying to do a sum from I equals 0 to the length of the plate minus 1. So if we're going to use I as our variable, we know that I should start at 0. Remember, when you have a summation, this is the last value that you want I to have. So you could say I is less than or equal to string length of plate minus 1. And the implicit understanding here is that we increment I each time through the loop. And so this will start with the first character of the plate, that's index 0, and it will end with element string length plate minus 1. And does that make sense? Well, make a test case. Here's hello. This is bracket 0. This is bracket 4. String length is equal to 5. So the last element of a string is always at index string length minus 1. That's why when we chop off a new line, we set element string length minus 1 to null. So if you want to include that last character, you want to include, the index of string length minus 1, right? Which is what the summation is telling you. It's saying run I from 0 to string length of the plate minus 1. So this will work. But if you do I less than string length plate minus 1, that's not going to work, because you're not going to use the last character in your plate. If you do I less than or equal to string length, that's not going to work. Well, it'll work, but it shouldn't, because you're also including string length, which is after the end of the string. Now for us, that's just a null terminator, so when you multiply by I plus 1 squared, it doesn't change anything. But for other hash functions, that could get you into trouble. You could also do I less than string length of plate. That should work fine. This and this are the same termination condition, because I is an integer. If it's less than string length, it's less than or equal to string length minus 1. So you can take it directly from the formula that you were given, right, for the hash function, but you can also, think about it different ways. All right, you had to allocate space inside list add for those strings, which most people did. If you didn't, then as promised, right, points were taken off. But in this node structure, right, plate, first, and last, these are just pointers to characters, but they don't have any memory allocated to them yet. So you needed to set them equal to malloc, and we said different times in class you have to malloc the length of the string plus 1 so you have space for the null terminator. And I warned you that if you don't do that plus 1, you end up setting up little things that will blow up later on. So that happened in a few cases, but most people did the malloc of string length plus 1, which is great. That's one of the most subtle parts of this whole assignment, and majority of people got that, which is good. All right, size of. So I keep saying this, I'm going to stop saying it really soon. Don't use size of with the name of a variable. Use size of with the type of a variable. If you have a struct node and you want to allocate memory for it, size of struct node. If you have a license plate, car star plate, and you want to allocate memory for it, size of car times string length of plate, maybe plus 1 if you want the null terminator. So a number of people mistakenly did size of plate. Does not work, because plate is a car pointer, and car pointers take 8 bytes. So plate could be 1,000 character long string. This will be 8, right? And if you allocate 8 bytes and you copy 1,000 characters into it, you overflow memory. And it may not crash your program right away, but it will corrupt data somewhere, and then later on you get a seg fault, or you get some weird output happening or something, and it's, tied to something that happened in a totally different spot in the program. So the easiest way to avoid this is don't ever use size of with the name of a variable. Only use it with the type of a variable. And yeah, if you go on Stack Overflow, you'll find the opposite advice. You'll find lots of arguments and so on. But to keep yourself from doing this kind of thing, easiest way to do that is just stick with using size of with types of variables. All right, hopefully that makes sense. Ask me about it more if not. So size of car star, size of struct node star, size of hash entry. Those are all good. Size of a variable, you're playing with fire. You can do it, right? There's nothing wrong with it. It's just more error prone. All right, what else? Lot of issues with formatting, which I decided not to get super duper picky on, for some reason, but yeah. Bunch of makefile issues. So it's good to use an existing makefile and just modify it to make a new makefile, but make sure that new makefile works, right? And this program in this case was called plate, but there were makefiles that were trying to make an executable called main, but had the instructions for making an executable called plate. And so if you run make twice, instead of saying everything's up to date, it recompiles everything and so on. So double check your makefile. Not a huge deal, just something to keep in mind. Some people had Dobby Elf take over their database, so every license plate became bad Dobby Elf, right? And Dobby is the last entry in the database file, and this is happening because most likely you're reading through the database file, you input a line, you've saved the plate first name and last name, and then in your node you say something like, you know, new arrow plate equals plate, right? Well, this does not copy the characters from here into there. This makes this thing refer to that thing. And if the last value that you assigned to plate when you were reading in your main program was bad, right? Then every node in every linked list is pointing to that same variable, and it sees the same value. And so you end up with 1,000 nodes scattered across 100 linked lists, but every node, even though it was created in response to a separate database, they're all pointing to the same 3 strings in memory, the same plate, first name and last name. And so what you want to do instead of this is string copy. And string copy is one of the weird C functions where the destination comes first. Most C functions, the destinations are at the end. But this copies from the second thing into the first thing. And it you know, looks at each character in here and copies it into here. So character by character at the end. This is still pointing to where it was, but it's you know, contains a copy of the characters that plate had. All right. Other thing, hashFind should not have to loop. So here's your hashFind function. And you're looking for the information corresponding to a license plate. And you know it's in one of your 100 linked lists. If you make a for loop and you go through every one of those 100 lists and call list find on each of those, that's an order n operation. You've lost the whole benefit of having a hash. With a hash, all you have to do is call list find on the appropriate linked list. Which linked list is it? It's the one that you get by hashing your license plate. So you take your license plate, you run it through the hash function that gives you an index. At that index in the hash table, that's the sentinel node of the linked list where this plate would be stored. And this is an order 1 operation, and this is an order 1 operation, and this is, you know, if the lists are small, order 1. And so that's where that whole efficiency of a hash versus just a big long linked list is coming from. And so when you add, or when you search, or when you delete, and we didn't delete, you move immediately to the linked list of interest by using the hash function. And we talked about this as a function, and really you want to write yourself a function called hash, which takes a character pointer and returns an integer. And then you use that inside hashFind. You use it inside hashAdd. If you had a delete function, you would use it inside hashDelete.
I've got a question about like converting characters to ASCII codes.
Yeah.
Like some specific library function that we can use for that, or does it like automatically do that?
All you need to do is something like plate bracket I, right? And that is the ASCII code of the ith character of that string.
Okay.
So characters are a little funny in C. They're actually like super short integers. They're 8 bits, but they're treated just like integers, which is why you can use them in switch statements. It's why you can return them from getChar, and it's also why you can use them, inside expressions by just saying plate bracket I. It just gives you back the ASCII code.
I think if you add 62 or something like that to a lowercase, it becomes an uppercase, or maybe vice versa.
Yeah, if you add 32 to uppercase, you get lowercase, but don't do that. There's a library called ctype, and you can do something like 2 lower, or 2 upper, or is upper, and so on. And if you ever need to do like case conversion in C, use these macros, right? Because not all systems use ASCII. And so, on an ASCII system, you can do the trick of adding or subtracting, or you can see if it's uppercase by seeing if the ASCII code is between 65 and 97 or something, 92. But not guaranteed to work, right? So these functions are written specifically for the system that you're running on, and they basically do that kind of ASCII arithmetic, but they're guaranteed to work. But it's fun and educational and good practice to play around with ASCII code sometime and do those kinds of things, right? Or flip bits in an ASCII code and see what happens. All right, and then there was an earlier question about can we talk about the hash table structure? So let's go through this here at the end. And the easiest way, I think, to think about hash tables is it's like storing everything in a linked list, right? So like PA1 without bothering to like order the entries. If you just imagine, take all your data stored in a big long linked list, right? And now if you want to search for something, start at the beginning and just move through, look for the thing. Inefficient, but it works, right? So if you want it to be more efficient, what you can do is have a bunch of linked lists. So if you have 1,000 pieces of data and you have 1,000 linked lists, chances are each linked list is really small. And so, searching through a linked list of length 1, really quick. But which of the 1,000 linked lists do you look through? If you have to look through all of them, you haven't really bought yourself any time. So here's, a bunch of lists. And we can label these list 0, list 1, list 2. And for us, default 100 lists, so list 99. And now if you want to search for a particular license plate, if you knew which list it would be in, right, you only have to search that one list. And so we have a map that lets us take a license plate, put it into this hash function, and the hash function tells us which list that plate gets stored in. So that's the mechanics of how a hash works. we're looking for something like a license plate. We know it's in one of these lists. Rather than check all of them, we have this function that we call a hash function, which takes the plate and tells us, oh, yeah, check this list right here. It would be in that one. All right, so that's the goal. The way that we make this work is, well, we need a hash function. That's just your function hash, which does that for loop and that summation and so on. And then we need a way to quickly get to each of our 100 linked lists. And so this is actually an array. So it's not quite a linked list of linked lists. It's really an array of linked lists. And so each of these things is a struct node star. And this is an array of struct node stars. So the hash table is really like this. It's an array of struct node star. Or if we were to allocate it dynamically, statically, we would do this. Here's an array of 100 struct node stars. Or if you take the advice and you say, hey, instead of a struct node star, I'm going to type def this to what I call a hash entry, then we could allocate a hash table as saying, hash entry star hash table, which says this is an array of hash entries. Or if we were to statically allocate this looks very familiar now. Hash entry, hash table, bracket 100. So what is this? Well, if I said int hash table bracket 100, it's an array of 100 ints. If I say hash entry hash table 100, it's an array of 100 hash entries. And we don't want to statically allocate it because we don't know how big the table should be, so we do that and we do a malloc. But we can think of it as being equivalent to doing something like this. And so now if I say, hash table bracket 5, that is a hash entry, which is a struct node star, which is a pointer to a node, which is the sentinel node of a linked list. How are we supposed to do the definition part of hash entry then? So hash entry is the type def, and it's purely a convenience so that we don't have to do the double star up here. But that lets us do let's see where my type def is. So if you type def struct node star to be hash entry is basically an abbreviation for struct node star. So each hash entry is a sentinel node, which is a pointer to a struct node. So now you can declare your hash table as just hash entry star hash table. And this is, literal C syntax. This is exactly how you do a type def. All right, I think that was it for main comments on PA3. And we're going to leverage some of this in PA4. And so you can reuse a lot of your main program. Some of the commands will be similar. Some of the parsing will be similar. And so if you implemented PA3 with a main program that just called your hash functions, it'll be a fairly easy transition to PA4 because you'll be calling a different set of functions basically to build and manipulate a database using trees instead of hashes. So we're not going to do anything more with hashes for PA4 or PA5. They'll pop up on the exam, but they'll definitely pop up in other courses. And so if you didn't figure out quite, how the hash part of this works, it's worth figuring it out, especially now while it's still fresh in your mind. Come by office hours and let's work through this with your code, and hop into GDB and so on and so forth. And if you pin it down now, then when you see it again, later at a university, it'll be old hat, and that'll be good. Most people figure this out, but if you're going to run GDB on a program that takes command line arguments, you have to do something, because if you just say GDB plate database.txt, GDB eats up that second argument, and so there's a few ways to do this. When you run GDB, you can say GDB -- args, and then put in plate data.txt, and that will run plate with this command line argument. Or you can do the usual GDB plate, and when you're inside, you can say run data.txt. Or when you're debugging, get rid of the command line arguments. Unless that's the part you're debugging, just hardwire the data plate name, the database name, so that you just run plate and it always opens up /temp/database.txt, or whatever database you're working with. Just hardwire that, and it'll make it faster to run your program, to get it going, to get to the bug, right? And it takes care of passing arguments to GDB and all that kind of stuff. Make life easier on yourself. So tweak things in a way that makes sense. But there's other ways, to get GDB to actually do that. All right. Any other questions on PA3?
So how could we have used switches for the star load and star dump and those commands, like parsing them? Because I'd always get like an error saying there was like no integer type equivalent or something.
Yeah, I'm not sure a switch helps in that case. Because the types of things we're looking for are mostly strings. So if you're looking for, a numeric command, if it's like, enter 1 for this, 2 for this, 3 for that, switch statement's going to work great, because you can just switch on the command. If you're trying to parse something more general, right, where, they could say, some long-winded command with multiple parts to it, think, like GDB, for example. Sometimes you say print X, sometimes you say step, sometimes you say list, sometimes you say list 10. Then you can start to do some things like, determine how many things were typed, and then do a switch based on that. So if they only type one thing, right, so case 1, and then put in your things for parsing, single word commands, and then case 2, and put in your statements for parsing 2-word commands, and so on. But a switch is really nice if you're trying to operate based on different values of an integer or a character, right? So characters are small integers. So like in PA1, where you had single character commands, a switch can work pretty well to do the initial parsing, to say, oh, they typed an I, okay, this is an insert command, and now you can put something in that does a scan to look for an integer after the I, and so on. But that wasn't the case here, right? We only had, 3 commands, and each of them was a string, and anything else was a license plate lookup. So I'm not sure a switch would occur to me as sort of a way to clean up the code for this. I think 3 if statements probably works pretty well. And then, if it's none of those 3, just go ahead and do a license plate lookup. Along the lines of parsing, break and continue are really nice things when you're in a loop. So most of our programs, we write these while loops. And so, maybe we do something like, well, null is not fgets, which calls fgets to read in a line and checks to see if we hit end of file. And so we can do something like, if this is a load command, do some stuff. And when we're done, if we want to go back to the top of the loop, we can just say continue, which says go to the top of the loop. Okay, why do we want to do that? Because now I don't need to say else. Now I can just say, new statement if string compare dump. Do a bunch of stuff, continue. And then I can do, my scanf. Do a bunch of stuff, continue. And now, if I get to this point, I know that I didn't enter a load or a dump followed by an integer. And so now I can do my hashFind. And then go back to the top of my loop. And if you don't do that, these all become else statements and they become indented over, and all of this stuff becomes a big else statement which gets indented over, and so on and so forth. And there's nothing wrong with that, but every level that you indent is kind of another thing you need to keep on your mental stack when you're writing the code and looking at the code and debugging the code. You got to remember, oh, I'm inside an else statement because this if failed, which was an else statement which was run because this if failed, which is an else statement which executed because this if failed, and you're exhausted by the time you get down here, So if I know this block of code will execute if the person types in load and go back up, and I know that if I get down here, I didn't have a load command, right? And so this is, just a first level indent, second set of statements to execute. And so that's just another way to organize it and kind of avoid, the increasing indent that sometimes pops up with parsing stuff. All right, so yeah, good answers in chat there.
Also, how do people go from, depending on the number of arguments, go from, fclose to, parsing user input commands? I'm just curious, because,
Can you say that again?
I tried using the go-to statement for going to my quote-unquote main loop after doing an fclose on a certain case for the database file. And I was just wondering if people did something different, or people definitely probably did something different, but I'm just wondering what that is.
Yeah, so there's a few main sections to PA3. So there's process, command line, arguments. So look at the command line, make sure there was a file name listed, make sure if there was a second argument it was an integer, figure out what that integer is. If there was no integer, use a hash size of 100, otherwise use that integer, right? So before you do anything else, you look at argc, argv, and you figure out what's the hash size supposed to be, and what's the name of the file I'm supposed to read. And then the second step is read the database file. And so this is usually a while loop. So open up with an fopen, make sure fopen, returns a good value, not null. And then while fgets doesn't return null, take the string from fgets. Most people use scanf with 3% s's to break it into plate first and last. Call hashadd to add that to your database, and so on and so forth. And when you get to the end of that, when fgets returns null, you call fclose on whatever your file pointer was. And now you're completely done with reading the database file, and so now you make another while loop, which is process user input. And your code can just kind of fall through from the end of this while loop, right after the closing bracket there, you fclose the file, and then go right into a new while loop. While fgets from standard in is not null, read the input from the user and go through and figure out what it is and do what they're asking. And I don't think there's any need to sort of go to another section. You can just put that right after this.
So do you do that for each startup case then? Like if int argc double equals 2, then read database file and then process user input, and then close bracket that, and then repeat for the int argc double equals 3. And
I would suggest do everything you need to do with your command line arguments argc argv first, and leave the result of that in some variables, so that after all of this you have a hash size, and you have database file name, right? And then regardless of whether they put in one command line arguments, two command line arguments, this file, that file, etc., right? We're done with that section of code, and now we do this single while loop which reads the database file and adds to the hash table, and it uses hash size when it calls hashadd or when it calls hashinit, and it uses the database file name when it calls fopen, and so on, and do your input and close, and then when you're done with that, do this while loop. And so it's really a set of code on the top with some ifs and conditions and scans and so on, and then that section is finished, and go on to your next section, which is a while loop mainly that reads the database file. And then when you exit that, close the file, all that part of your code is done, and now the bottom part of your code is the main while loop that reads user requests and does lookups and so on and so forth. And then when that exits, you can have one more step, which does hash free and says goodbye or whatever you want to do, right, and exits the program. Does that make some sense?
Yeah.
And I've seen more than a few students do what I think you're describing, which is have a section that says if argc equals 1 or equals 2, right, meaning that they didn't specify hash size, and then there's a whole program for a hash table size of 100, right, and that's all in an if statement. And then there's an else, if argc equals 3, and there's a repeat of all that code that includes, parsing the hash table size and using that, right? And that'll work, but it's a lot of redundancy. And so if there's a way to sort of, keep that part that's the same as, just a single copy of that code by doing the pre-processing ahead of time, that makes the code a little easier to deal with. The other thing is, you know, each of these could be a separate function. And if you do that, you have to get, you know, fluent in passing arguments to functions and bringing values back and so on. But your main program could be, you know, 4 statements: process command line arguments, read database file, process user input, finish up. And each of those could do, you know, the appropriate thing. And you have to pass a lot of information back and forth to make that work, but that's another way to do it. And then your main program is, you know, a really small thing.
And then the rest of your main.c file is just like those functions.
That would be those functions, yeah, for doing these things. And that's nice to do sometimes. Sometimes it's really nice when you have, you know, a 2,000 line program and your main program is 4 lines. It's kind of a nice way to sort of like take the other, you know, 1,996 lines of C code and sort of put them out of view. I've got something I'm working on that lays out like that right now. It's kind of fun. All right, any other PA3 questions, comments? All right, let's do a 5-minute break. We'll come back and we will launch into PA4. And PA4 is a fun assignment, so hopefully it'll be satisfying to work on and super satisfying once it works. So we'll come back in 5 minutes and
In their own way.
say again?
What? They're all fun.
They are fun. PA4 is especially fun. All right, so I'll see you back here in a few minutes. We're back. My coffee is still microwaving.
Oh, good idea. Coffee.
Yeah,
BRB.
decaf I made this morning and it's like cold, so I'm heating it up. It's pretty righteous.
Decaf.
I know why, but it's what I do.
Well, I suppose when you get a bit older, I guess. I don't know.
I have been dabbling in like regular Coca-Cola though lately, so it's the dark side. All right, 1 second. All right, let's go on to PA4. So PA4 is going to feel similar in a lot of ways to PA3 because guess what? It's a license plate database program. How exciting is that? All right, so same drill as before. So we have a flat file of license plates, first names and last names. We're going to work with actually the same sample file on the same location on the server, so you can keep using that one, or your own version of that file if you want to work with a smaller file. And you're going to make a program called plate, and you run it by saying plate followed by the name of a database file. All right, there's no optional argument here because we're not building a hash table this time. We're building a binary search tree. And so your program is going to open the flat file that you specify, read it in line by line, break it into 3 fields, plate, first name, last name, and build a binary search tree out of that information. All right, so it's going to start with an empty tree, right, a root which is just null, and as you read each line, you're going to create a new node containing the plate, first name, last name, and then you're going to add that to the tree using the algorithm that we went over last week, and we'll talk about it again this week. And so you're going to construct this tree in memory that contains all the license plate information. All right, so it's keyed on plate. So, you know, BSTs are alphabetized basically. And so the plate is the thing that we're using to search. And so that's the key you're going to use when you're deciding whether you insert to the left or the right of a root. And let me mention right up front here, when we're alphabetizing, use string compare. Right? So if we say string compare cat, dog, that's going to be less than 0. It's less than 0 because cat comes before dog. If you string compare dog, cat, that's going to be bigger than 0 because dog comes after cat. And if you string compare cat with cat, that's going to be equal to 0 because those two strings are equal. So when we do binary search trees with integers, we're always saying if the number's smaller than the root, go left. If the number's bigger than the root, go right. For strings, we're going to say if string compare of your string with the root is less than 0, go left. If string compare of your node with the root is bigger than 0, go right. If you're searching for a node, if string compare is equal, then the node has the same string. All right, so that's the only weirdness with strings versus integers. Well, it's one of the weirdnesses.
We're gonna sort it by alphabetical.
You're going to sort it alphabetically by license plate. Sorry, I cut you off at the end.
Oh, no problem at all.
All right, again, inside your nodes, you're going to need to dynamically allocate space for the plate, first name, and last name, because those are just car pointers, and you're not allowed to just, statically allocate big character arrays there. So do the thing you did in PA3, but remember to malloc based on string length of the thing, and remember to add 1. Right, so So malloc using string length, and don't forget to add the 1 for the null terminator. Alright, and then after you open the file, read in all the data, build your binary search tree. When you're done, close the file with fclose, and then go into the user interaction part of the program. So same thing, the person's going to type in commands or license plates to look for. There's only 2 commands the user can type here. There's no load command, because that's a hash table thing. So they can say dump, which will display the entire contents of the tree. And there's specific dump requirements that we'll talk about in a minute. But you can also delete data from the database. So you can say *delete followed by a license plate, and that will delete that node from the tree. So this is a new command beyond what we had in PA3. I should have put that in PA3. That would have been fun. So yeah, you can say *delete, put in the name of a plate. That should remove it. Anything else other than Control-D should be taken as a license plate lookup. If they misspell a command, if they just hit Enter, etc., that's a license plate lookup. If they hit Control-D, that should exit the program. Alright, when you do a license plate lookup, output the information like this. And I want to see it in this format. I didn't take off points on PA3 for different formats. I want it in this format. First name, name, last name, name. Right, so separate lines, separate fields. Alright, if you say *dump, it's going to display a bunch of information about the tree. Alright, so what it should do is you should print out tree height : and tell me what the height of the tree is. We're going to talk about how to find tree height later on. And then print out the word balanced : and print out either yes or no, depending on whether or not the tree is balanced. We're going to talk about what it means for a tree to be balanced and how to check it later on also. And then I want you to print out the results of traversing the tree 3 different ways. And the first one should be left node right, in order traversal. The second one should be pre-order, the third one should be post-order. And please do them in this order. I may take off points if you don't. Depends what mood I'm in. But I want to see the in-order traversal first, and then the pre-order, and then the post-order. And that's the whole dump command. So it basically prints out the tree height, prints out a report on whether it's balanced or not, and then prints out 3 traversal orders, starting with in order, and then pre-order, and then post-order. Right, so the output format and the output order matters. And then the only other command is delete. So *delete followed by a plate should try to remove that node from the tree. And your result is either the word success if you succeeded, or the word plate not found, uppercase, if you did not find it. Alright, there's a sample program on the server. We'll run through that in a few minutes. You can use that to compare what your program should do. Alright, I strongly recommend that you make yourself a small database file to work with. If you decide to work with a 1,000-line database file, your *dump command is going to produce over 3,000 lines of output. That's not a fun debugging session. Do that when you think you're done. When you think you've got all of this nailed down, then work on the large database so you can compare it, to a really big test case. But make yourself a small database file with, 5-6 names in it. And you can run that on the test executable on the server. You can run it on your executable and compare outputs. And you get, 24 lines of output. It's a lot easier to work with. If you want to know if you're mimicking my output exactly, you can run, your code, run the sample code, redirect the output to a file, and then use the difference command, right, diff. And that'll tell you if there's any differences in the output. Now, you're not required to match every single nuance of my output, right? If I put a period after plate not found, you're not going to lose points for that. If you put plate not found in lowercase, you're probably not going to lose points for that. But if you want to, guarantee that you're producing this output exactly the way that I am, right? You can use the difference command to see that, and it'll do a character by character comparison. And you know, if you can reproduce every aspect of my output file exactly, you got a pretty good bet that you're outputting the right stuff. And then it's a question of, you know, are you doing it in the right way internally and so on. But that's, you know, that's like the highest bar to reach for as far as output format. Alright, when you hit end of file, which means Control D at the beginning of a line, or if you're ingesting commands from a file, when you hit the end of the file, you should free all the memory and then exit. Okay, and that's the only way that you get out of the program. Alright, so let's look at sample execution of this. So there's a sample executable on the server called /temp/plate4. And I can run it on our big 1,000-line database file if I want. And so it says enter command or plate. It's already read this file in and built up the hash table now. Right, so that's sitting inside memory. So I can say, you know, let's look for a license plate, and it should tell me who that license plate is. So there's some vanity plates that are in there. And if you know, have something that's not a plate, it should say plate not found. If I delete more cheese, it says success. And now if I try to look up that plate, plate not found. If I try to delete a plate that's not found, it says plate not found. If I type anything other than one of those legal commands, it's a database lookup. So it's looking for a plate. Alright, so the dump command will produce a lot of output. Probably more output than we want to scroll back through. So the dump command printed out tree height 21. So longest number of hops from the root to a leaf node is 21 hops. And is the tree balanced? No. It's pretty severely non-balanced. And then the in-order traversal. And you can confirm that it's an in-order traversal because the license plates are coming out alphabetized. Starting from AAM, there's our A's, there's our B's, there's Dobby, and so on. And an in-order traversal should always come out alphabetized.
Why is it a tree not balanced?
Because unless you work pretty hard, your tree won't be balanced. And so we're going to go through inserting into a tree and do some examples of that, and you'll see that generally you end up with an unbalanced tree. Unless you're really lucky about how the data arrived. So the in-order traversal is alphabetized A to Z, and then node left right. Left right node, there's no clear intuitive explanation for this ordering. It's based on how the tree was built, but you know, you can compare it to the sample code and see. And again, you know, it's best to do this on a small database file. So here's a post-order traversal left-right node, and then we go back to enter plate or command.
So for this program, we're not actually worried about balancing the...
No, you do not want to balance the tree.
Okay.
Alright, and then when you're done, you can just do a Control D, and that should free the memory. And if you run this through valgrind, right, you can do all the usual stuff. When you Control D, it should come back, all heaps were freed, no leaks are possible. Alright, and you should not be getting, you know, valgrind messages while your program is running. It should be totally silent until you exit, and then it should give you a report at the end of your program's execution. And that should say 0 errors. Alright, so Make yourself a small database. Right? 5 lines. And, you know, now if I say star dump, I've got something that doesn't terrify me to look at, you know, scrolling off the top of my screen. It's only got 5 license plates in the database, so, you know, there's the in-order traversal, there's the pre-order, there's the post-order. And just for kicks, let's see what this tree actually looks like if we build it. So let's look at our database file. And it looks like the first letter is unique. N, B, W, Q, and O. So I'm not going to write out these whole license plates. I'm just going to use kind of, well, I can write them out. But let's see what happens if we were to build a tree by hand ingesting this data. So the first line we're going to read is NWL535. And since our tree is initially empty, that's going to become the root. Alright, so there's the root of the tree. And then we read our second line from the file, and that's BHC709. So where should I store BHC709 relative to the root?
To the right of it.
So BHC709, so we start at the root and we compare what we're adding to this and we see if it's less than or greater than. And if it's less than, we're going to go to the left. If it's greater than, we're going to go to the right.
Oh, okay.
So BHC is less than, so yeah, as someone said in chat, store it to the left. Alright, so that's what our tree looks like after 2 lines of our file. Now we get to WKK618. Where should that go?
So that would go to the left again.
So WKK, so start at the root. Yeah, start at the root, and W is bigger than N, so this will go to the right. We don't actually have to do this. The program's going to do this for us. But we want to be able to mimic what we think the program should be doing so that when we run into problems, we can look at what the program did and see if it matches what we thought it should do. So we want to be able to construct these by hand. Okay, so now it gets trickier. We got our 4th plate, QSC. And so where's QSC going to go?
To the left of the right node from root.
You got it. We're going to start here. Q comes after N, so we're going to move to the right. Q comes before W, so we'll move to the left. There is nothing to the left. This is where QSC 375 should appear. All right, last one, OWF. And so where does O go?
To the right, and then to the left, and
then we got to sing the alphabet song in our head. So yeah, O comes before Q, so it's going to go to the left again. So we start here, we go to the right. O is smaller than W, so we go to the left. O is smaller than Q, so we go to the left. It'd be a cool short story about, like, the world wakes up one day and nobody can remember the order of the alphabet. And, like, how many things break because of that. So there's what our tree looks like, right? And so we can tell it doesn't look very balanced. right? Because we've got one thing hanging on this side, and we got 1, 2, 3 things on this side. Now that doesn't necessarily mean it's unbalanced, but it turns out this is unbalanced. And it's just because, you know, of the way that we happen to get this data from the incoming file. So balanced no, tree height is 3. Well, from this root, we can take 3 hops, 1, 2, 3, to get to the deepest node. So that's what the tree height equals 3 is reflecting. The in-order traversal should be alphabetized. That's fine. If we do the pre-order traversal, how is that working? It's saying first we should print out the root node. So this will come out first. And then we should traverse the left tree. And then we should traverse the right tree. To traverse the right tree, first we print the root node. And then we traverse the left tree. To traverse this tree, first we print the root node. And then we print the left subtree. And then we would print the right subtree. So the pre-order traversal should be NWL, right here, followed by BHC, followed by WKK, followed by QSC, followed by OWF. The post-order traversal would say, well, let's first traverse the left tree, so this will come out first, and then let's traverse the right tree, and then print out the root, so the root will come out last. How do we traverse this tree? Well, first we traverse the left tree. And how do we traverse this? First we traverse the left subtree, so this will come out second. And then the right subtree is null, and then this one comes out third. And that's the whole left subtree. Then we would traverse the right subtree of WKK, and then we'd print out the root, which is fourth. So the post-order traversal should be BHC first, followed by OWF, followed by QSC, followed by WKK, followed by NWL. So as you get more comfortable with traversing trees by hand, and it's not a obvious thing to know how to do, but if as you get comfortable with that, right, you can compare these traversal orders and kind of confirm that, you know, this output does correspond to this tree. And you know, when you're working with a sample database, you know, make your life easy. You know, make your license plates like A, B, C, D, E. And now, you know, it's a little easier to work with. So, by the way, what does our tree look like in this case, where my data came in A, B, C, D, E? So A is the root node, and then I read a B, that should go to the right of A, and then I read a C, that should go to the right of B, and then I read a D, that should go to the right of C, and then I read an E, and that goes to the right, to the right, to the right, to the right. Right? That's my most unbalanced right lopsided tree that I could possibly have with 5 nodes. And the height, you know, the number of hops to the deepest node from the root looks like 1, 2, 3, 4. So there's the height of 4, and it's not balanced. And the in-order traversal is always alphabetized, but if I traverse by printing the node first, it's also alphabetized because it's just a linked list. And if I traverse by printing the root node last, it's reverse alphabetized. Because first I'm going to go all the way to the left while there is nothing. Then I'm going to go all the way to the right, and then I'm going to print the root node. And I'm going to pop up one more and print the root node, and so on. And so as you develop this program and you are confident that it can traverse, or, you know, if you want to use the sample program, you can use this to study traversal orders and this recursive traversing algorithm that we're talking about, and play around with this and sort of you know, test and develop your understanding of things. This is all stuff that's not part of the assignment, right? But if you're spending time outside of class trying to understand what we're doing in class, right? These are just some of the things you can do. You have code that will build a tree and then tell you things about it, right? That's a great source of examples to work with. All right, so let's talk about how we implement this. So how do we actually write C code to do all of this stuff? First thing you need is the node structure. So the nodes of the binary tree are set up like this. First comes the data field. So there's a plate, a first, and a last name. Those are pointers to characters, just like the nodes in PA3's linked lists. And then there's a left and right field, which are pointers to the same struct nodes. So it's data, and then left child pointer and right child pointer. And I'm going to type def a struct node star and call it an uppercase node. So a node with a big N is a pointer to a struct node with a small n. And the idea is I don't want to keep saying struct node star, struct node star. I want to just say node with a big N and understand that that's a tree node, but it's really a pointer to it. And that's mostly what I'm going to use in my code. So for example, declaring the root, declare it as a node with an uppercase N, because the root is a pointer to a struct node. But we're just going to think we've got a new type of variable called an uppercase node. So initialize your tree by just saying, you know, node root equals null. That's your whole tree initialization. Because an empty binary tree is, you know, a tree that's null. All right, so we're going to talk about height and balance first, or later, right? Height will tell us the height of a tree. Balance will tell us if the tree is balanced or not. We'll get to those in a bit. So you want an add function, and your add function takes the root of a tree and then the plate, first name, and last name. Build a new node, allocate space for those strings, string copy from these strings into those, you know, fields you allocated space for in the node, and then do what you need to do to add this node to the tree. And the add function should return a node. We have a fresh showing up sometime, by the way, so don't be startled.
Okay.
All right, and then we return a new root of a tree from the add function. So we talked about this last time, but we'll go through this again this week. And so when you want to add a node, you know, just call the add function with the current tree root, pass first, plate first and last, and set your root equal to the return value. When you want to search for something, take the root of the tree, pass in the plate, put in placeholders for first and last, right? So big, you know, beefy character arrays, and check the return value. If search returns 0, it's not found. If it returns 1, it found the plate and it copied the first and last name into these variables. And then you can go ahead and print them or do whatever you want to do. And then delete, which we haven't talked about yet, deleting from trees, but we will. Pass the root of the tree, tell it the plate you want to delete, and return the root of the new tree after that node has been deleted. Right? I strongly recommend that in your delete function you call search, or do something, you know, to see if this plate exists in the tree, and if it doesn't, don't bother trying to delete it. But we're going to talk about delete probably Wednesday. I don't know if we'll get to it today. We might. And delete is a whole separate algorithm. All right, 3 traversal functions. I'm calling them LNR for in order, NLR for pre-order, LRN for post-order. These take a root, they don't return anything, and they just go through and they traverse the tree and print out the data in the required format. And then a tree-free function takes a root, does not return anything, releases all the memory associated with the tree. And we'll have to talk about how to do that, but it's going to be very similar to what we did with the list. All right, that's it for required functions. Now you're going to have more functions than this. Depending on how you decide to write your main program and set things up, you may have a lot more functions, you may have a few. But at the very least, you're going to want, you know, these functions for interacting with and manipulating the tree. And then your main program is going to be, you know, again, just a bunch of calls to these functions under different circumstances. And the shared area section on the Linux server has, you know, sample code that we did last week, showing, you know, some of the startup for these kinds of things. So this is a node of integers with the integer in the middle, right? But it's the same idea, right? So here's how we're using the add function, initialize to null, and then just keep calling add. And here's a working add function. This is recursive, right? And it's 3 statements. If the root's null, make a new node and return that. Otherwise, if the data goes to the left of the root, add the data to the left of the root, set the root to point to that, and return the root. Otherwise, add the data to the right of the root, set the root to point to that new node on the right, and return the root. And here's a sample in-order traversal algorithm, 3 lines. Right, traverse the left subtree, print the root data, traverse the right subtree. So that's on the server, right? And it's under tree code 1 in the class from Thursday, the afternoon class. We did similar code, and that's in this directory. So, you know, you can use that as a starting point, but any time that you use code from a server, you really want to be sure you absolutely understand that code. Don't just copy it and start trying to use it for a week and then scratch your head and say, yeah, I never understood what this code does, right? Write the code yourself, but you can lean on the sample code to kind of like help guide you. But write the code yourself, and after you've written it and you've got it working, come back later, try to write it from scratch, right? The idea of the algorithms that we're using for these tree manipulations should become solid enough that you can sit down and you can recreate this code for tree add, tree search, and so on, you know, starting with nothing except your understanding. All right, so suggestions. I always make lots of suggestions. I don't know if they help or not, but I'm going to make suggestions anyway. Suggestions, you can start off.
So much.
Say again?
But they help lots. They help tons.
Okay, cool. Start by, if you want, just make a tree inside memory, right? So I shouldn't have closed this out so quickly. Start by just cobbling together a tree. And you know, we did this thing originally in our first version of this sample program. We just made a node for the root. We set the left child to be a 20 node. We set the right child to be a 60 node, and so on, right? You can do that in here. Start by cobbling things together. If you want, you know, start with a tree of integers, because there's an extra layer of complication dealing with strings and allocating memory and all that kind of stuff. So if you want, you know, start with integers. And forget about database files and command lines, right? Just work on the tree stuff. So cobble a tree together and you know, get a set of code that builds a tree with, you know, half dozen nodes in it or something, and work on your traversal, right? Do an in-order traversal. And if you do this correct, you should see the data you put into your tree appearing in order. Well, now you can, you know, change around the numbers in your tree, right, and run your code, and you should still see the numbers in order, right? And this gets you good at drawing pictures of trees, gets you good at thinking about left, right, and right, right, left, right, and that kind of stuff. And it tells you your traversal code works. And you want your traversal code to work because you're going to use that as you develop your other functions to see, what your tree looks like. All right, if you want, you can go ahead and do node left, right node. Be careful with these, right? They look very, very similar to each other, but if you go a little too overboard with copy and paste, you can copy and paste more than you wanted and forget to change things. So, make a small tree with a handful of nodes and make sure it's doing the right thing. Here's a really simple tree. So if I do this in order, I should get 10, 20, 30. If I do this pre-order, I should get the node first, and then the left, and then the right. If I do this post-order, I should do the left, and then the right, and then the node. So that's like a first-level test on your 3 traversals. But, if you don't want to do these other traversals right now, don't worry about it. They're not going to help you a whole lot with debugging. They need to be done at some time. But if you forget about them and you suddenly remember, 10 minutes till 8 next Friday morning, you may make mistakes when you try to code these up. So, do them sometime, but you don't need to do them like right up front. But you want your in-order traversal pretty early on. All right. Search is a pretty good one to do next. And search, is this recursive function. If our number matches the root, we're done. We found it. If the number is less than the root, return whatever searching the left returns. Otherwise, return what searching the right returns. All right. And around this point, you might start switching over to strings. Because now, you've got a way to traverse. You've put together some nodes. You're doing search. Now start thinking about using the actual node structure and have, a play to first name and a last name. And so make a search function and don't worry about, anything fancy with user input and parsing and so on and so forth. You can test your search function with something like this. Just search root, comma, someplate, comma, first, comma, last, where first and last are just, empty strings. And if result equals 1, print a message saying, hey, I found your string. First is equal to and print out first. Last is equal to and print out last. Otherwise, print out not found. And now write the same code, but search for some other plate. So if you're building your tree with, these 5 plates, I could make this first statement, search for NWL535, which I know it's going to find because that's the root. And then I could search for, BHL709. And then I could search for QSC375. And then I could search for, garbage, a plate that's not found. And make sure it says not found. And I'm not doing command lines. I'm not doing argc, argv. I'm not, doing scanfs. I'm not doing fgets, right? And I'm not typing anything while my program runs. This is just a hardwired test bed, right? So test beds are key, right? A test bed is a main program whose purpose is to exercise some part of your code. And the best test beds, you just type the name of the program, run, and you can look at the result and say, did it work or not? Right? It's a little bit how I grade some of your assignments. I make my own test bed, I link in your code. And so you can, if you're developing the search function, write a test bed that looks something like this. You do some initialization, you add some nodes to your tree, and then start calling search. And you know that it should say, this is whatever that first name was, this is whatever that second name was, this should say not found. And if you're not seeing that, or if it's seg faulting, or if it's going into an infinite loop or something like that, right, then you can run it in GDB. And you don't have to type things in when it's running or put in command line arguments or things like that, and you don't have to wait for it to read 600 lines of the file until it gets to the point where it misbehaves, right? Somewhere in this small number of lines is a problem, and maybe this first thing was correct, and this was correct, and this thing had like hung up horribly, or it seg faulted. So, you know, you do a next, 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 next. And when you get down here, you do a step, and you start going through your search code, and so on. So when you're done with PA4, you could have had, you know, maybe 20 different main programs that you wrote along the way, used to test a piece of code, and then discarded and continued developing. And you really, really, really don't want to develop this, you know, all at once, get all of your code written, and then say GCC for the first time, right? It's a really difficult way to work on large projects. So I keep saying this, and I'm going to keep saying it. Build this thing up in pieces. Start small. Pick one part of it that you want to develop, and develop it, and write a main program to test that. And forget about everything else, right? If you're just going to worry about, you know, ingesting the database file, just write a program that opens a file, reads it in, breaks it into 3 fields, prints out those 3 fields with delimiters around them so you know you're reading them correctly, and then at the end of the file closes it and says goodbye. And now you can run that, you know, on a few different files and see what it does, and if it seg faults in some cases, or it blows up if there's only 2 things on the line or something, right? You've got this nice little contained thing that you're going to debug and develop. And if you're working on the piece that, you know, adds things to your tree recursively, just write a main program that just, you know, keeps calling add and prints out the tree after each time. And, you know, if there's a problem with the add function, you'll find it in this little, you know, 10-line main program instead of this 500-line PA4 program where there could be, you know, 5 or 6 different things going wrong. So do this in pieces. Build it up. Alright, so I got another note in here just for kicks, right? This is a really good chance to play more with VI. If you're not very comfortable with VI, when you're writing stuff like this, right? This chunk of code, and this chunk of code, and this chunk of code, really similar to each other, right? When we build a tree by calling add, you know, 15 times, it's the same statement over and over and over again. We just change the number that we're putting inside the parentheses of the function call, right? And you can copy and paste with your mouse, right? You can copy and paste faster with VI. And this is a chance to play around with that. So just some ideas, you know, if you type 4 with an uppercase Y, that will copy or yank 4 lines from your file at the current location. So, you know, VI, let's just get some stuff in here. Let's say I wanted to repeat these 6 lines, right? So I'm not in insert mode, right? You never want to be in insert mode except when you're inserting. But I'm just going to type a 6, and I'm going to type a shift Y, and it says 6 lines yanked down here at the bottom. All right. And then if you type P, it will put those or paste those at that current point in the file. So if I wanted to copy those 6 lines right here, I can move down and just hit a P, and there's a copy of it. And I can move down and hit a P again, and there's another copy. And if I do a shift P, it will insert right before my current location, so I can shift P a bunch of times, and now I've got, you know, a whole bunch of copies of this. And if I wanted to change, you know, my return, I can say /return, get down there and change this to, you know, something I want to do, and then I can hit an N to get to my next return, and change that to my next statement, and do an N and change that to my next statement, right? And so you can do coding where you're taking some set of code and replicating it and making changes to it, right? Very efficiently in a good editor like VI. And so there's a lot of opportunities in this assignment to do that. When you write your traversal code, the 3 orders of traversal, very, very similar code to each other. And so, yeah, you can type it in, you know, 3 times, or you can copy and paste with your mouse and so on. But you can also do it with commands inside VI, as long as you're in command mode. So that's something to think about, you know, if you're looking to shake it up and make it more exciting, you know. All right, more suggestions. So after you've got search working, now you can do your add function, right? So up here we were building our tree by hand, but now do the add function. And we've got, you know, sample add code on the server for an integer tree. So how do you change that to code for a character tree where you've got strings? Well, you know, use string copy instead of equals, use string compare instead of greater than less than, and it's pretty much the same. And you've done this in PA3, right? You had to do string analysis and manipulation, and so it's more of that. And again, you still don't need to be ingesting the file. You can just, you know, call your add function with the root of the tree, the license plate, first name and the last name. And then change your tree traversal to print out, you know, those 3 strings with delimiters and tags in front of them so you can recognize them. And now you should be able to add a bunch of data into your tree, and you can call these add statements in any order you want. And when you do this in order traversal, the plates should come out alphabetized. Right? You get to that point, you're like way past the halfway part, right? You've got most of the tree system working at that point. All right, so yeah, initialize your root to null and call your add function. All right, once that's working, now you can ingest the database file. Well, this is a repeat of what you did in PA3. Use fopen on your database file, make sure it does not return null, call fgets, use scanf with 3% s's to get the plate first name and last name, and then pass those to your add function. Save the root, do that in a loop. When you get to the end of the file where fgets returns null, call fclose on the file pointer, and bingo, your root should have 1,000 nodes in it, or however big your database file was. Now you got a big tree file to work with, and you can hardwire some search tests and some traversal output and so on and so forth. All right, then we're going to get to height and balance, and we still have to talk about what these mean. I think we'll get to at least height today, and we'll talk about balance next time. But these are functions you're going to write, and there are a few lines of code. They're recursive. The height function includes a max function, but there is no max function in C, but I'm going to use max in pseudocode. And the idea is max AB returns the largest of A and B. If A is bigger, this means A. If B is bigger, this means B. If A and B are the same, it means A or B because they're the same, right? And when I do assignments that you know involve finding the max of 2 things, sometimes students get lost. Right? They go way down a Stack Overflow rabbit hole looking for, you know, where the max function is and so on and so forth. All you're trying to do is find the bigger of 2 integers, right? Or 2 strings or something like that. So, you know, it's an if statement, right? If A is bigger than B, do stuff when A is the max. Otherwise, do stuff when B is the max, or when they're equal, right? So my message here, right? This is your world. When you're programming, you're creating a little universe, right? And you are the creator of that universe. You set all the rules. You decide, you know, what's going to happen, what the purpose is here, and so on and so forth. And most of this is your choice. There's a few guidelines we have to obey, but you pretty much get to decide how you're going to do things. And as long as you accomplish your goal, right? That's fine. So if your goal at some point is to find, you know, what's the larger of A and B, you know, write an if statement. If A is bigger than B, then do this stuff. Otherwise, do that stuff. Or, you know, you can make a function that returns the maximum of AB and then say if A equals maximum AB, or you know, you can download a library and compile it in and link it and all this kind of stuff. But, you know, whatever you're into, but usually simpler is better. Right? All right, so after all that, then I would suggest going to your main program. Why? Because 1, your main program is largely already available from PA3. 2, your main program is mostly 224 stuff, so it should be pretty old hat. And 3, your main program is not necessarily what you want when you're developing these other functions. You want small targeted test beds that you don't have to type a lot of input for, and so on and so forth. So once you think your tree is working well, now do your main program, right? So parse the command line input, read in the file name, make sure it's a file you can open, add your data to your nodes. When you're done, close the file pointer, use fgets to get commands from the user and parse them out. If it's a dump command, call your balance and height functions and print out the results from that, and then call your 3 traversal functions. If it's a delete, call your delete function, but we're going to do delete at the very end. Otherwise, take whatever they typed in, pass that as the plate argument to search, look at the return value. If it's 0, say plate not found. If it's 1, print out the first and last name. Alright, once all that's working, you can go ahead and work on freeing your memory too at this point if you want. Then we're going to do delete. And delete we'll talk about on Wednesday. And that's the trickiest part, right? So and if you mess up in your delete algorithm, lots of weird things can happen. You can create loops in your tree that cause your search function to never return. You can, point to things that shouldn't be pointed to and get seg faults and so on. And so this by itself can introduce a lot of odd behavior. You'd like to know that odd behavior is coming from the delete function, instead of coding all of this and you get a seg fault and it's like, is it the add, is it the search, is it the free, that kind of thing. So I would work on delete last. As usual, ask questions if you're stuck or you're not sure how to start or how to proceed beyond some point. But do it in small steps and build it up. Alright, so your submission is pa4.tar, uploaded to Canvas by the deadline. I want you to include a well-written makefile as usual, so selective compilation plus a clean option. Selective compilation means it only compiles things that have changed, and once it's built the executable, if nothing's changed, saying make should not compile or link anything else. It should say everything's up to date. And in the tar file, include all the source code, including any .h files that you make and your makefile. And test the heck out of this before you submit. Right? I'm still getting submissions that, have last minute changes and the person didn't try making after they changed, and there was, a missing semicolon and nothing compiles. So when you're all set, copy your tar file to an empty directory, untar, make, test it, and then go ahead and submit. Alright, I am giving you a grading rubric here, so the assignment's worth 100 points. And I'm listing things that will cost points. Alright, you will not get a negative grade on this, but these deductions can add up to more than 100. So here's the things that I'm going to be testing and looking for. So you have to submit your program. If you don't submit it, you don't get any points. If there's any issue with the makefile, that's 10 points. If I can't compile or if I'm getting errors from the compilation, that's at least 40 points. And then if I can fix it, I'll keep grading. If I can't fix it and can't run your program, then you lose most of the points. Any warnings from the compiler, 10 points. If it cannot read the database file, that's 50 points off. So, obviously we need to be able to read the flat file and pull in the data to build a tree. If I give it a file that it cannot open, it should, handle that appropriately, something other than just seg faulting. If I run it without a command line argument, that should give an error message. It shouldn't just seg fault. If I can't look up license plates, that's at least 30 points off. If you're not building your search tree correctly, so maybe you're just building a linked list in memory or something like that, that's 30 points off. If you don't use dynamically allocated memory, that's 15 points off. Most people are doing, string length plus 1 as an argument to malloc. That's what you want to do. Yeah, no submission should be minus 100. Delete command is worth 15 points. That's the hardest part of the assignment, right? The hardest small piece of the assignment. The whole assignment is challenging. But as far as individual pieces, delete's probably the hardest individual piece. So it's only 15 points if you don't get that working. But if you don't get delete to work, right, make sure the rest of your program works. Don't sacrifice the behavior of your entire program just trying to get delete to work. If it doesn't work, just comment out the offending code, take the 15 points. If you're not using the delete algorithm that we're going to go over in class, that is 10 points off. There are lots of ways to delete. And you might be deleting it, it might be successfully deleting the tree, but if it's not using the algorithm we go over, you're going to lose points. Okay? Why? Because I want to make sure you understand this particular algorithm. Alright? Star dump command, if you don't implement that, that's 60 points, because now in order to test your code, I got to go in and I got to write my own main program and use that against your code. Height and balance functions not working correctly, 10 points each. Any issue with the traversal order, 10 points for each. Any valgrind issues, including any warnings or memory leaks, 15 points. So I'm upping the game here on memory issues. Control D should exit the program. That costs 10 points if it doesn't. If you interpret anything other than this as anything other than a plate lookup, that's 10 points off. Empty lines also should be treated as a plate lookup, so that would lose these 10 points up here. Any issues with the output format, 10 points. All right. And yeah, that's a typo on the 100 versus minus 100. So yeah, don't submit, you get 100. All right. Questions? Yeah. If this was a technical writing class, I would actually do that maybe. Like, see if you'd catch that, and then by turning nothing in, you'd get 100. All right, let's talk about tree height, because this is a fun algorithm. So here's a tree. And so remember, the height of a tree is the number of hops from the root to the deepest node, where the depth of a node is the number of hops from the root to that node. Yeah, you do not get negative points on PA4, right? So the lowest grade you can receive is a 0, but there's no reason these have to add up to the total number of points, right? So there's different things that cost you points, but it won't go negative. All right, so the depth of a node is the number of hops from the root to the node. And so these are depth 0, depth 1, depth 2, depth 3, depth 4. So the height of the tree is the depth of the deepest node, so start of the root. 1, 2, 3, 4 hops to these deepest nodes. So the whole tree has a height of 4. And we could think of, ways to do this by starting at the top and moving through and traversing and keeping track of the deepest spot that we've traversed so far. But there's another way we can think of height. And the way we can think of height is, here's my original tree. There's 2 subtrees. There's a tree over here, and there's a tree over here. And whichever one of these trees has the biggest height, the height of the original tree is 1 more than the height of that subtree. Because the distance from the root of this subtree to any node is exactly 1 less than the distance from the original root to any node in that subtree. And so the height of a tree with a given root is equal to 1 more than the largest of the height of the left subtree and the height of the right subtree. And that's a nice recursive definition of height. The height of an entire tree is 1 more than the maximum of the height of the left subtree or the height of the right subtree. Does everybody see why that works?
Yes.
Yep.
And it's definitely recursive, right? Which you know feels differently depending on where you are with recursion. But logically, right? This tree over here has a height of 3. This tree over here has a height of 2. So the deepest node in the entire tree is in this left subtree. And if it's 3 hops from this root, then it's going to be 3 plus 1, 4 hops from the original root. Where are you going?
Somewhere different.
Okay, no, I'm good.
Okay.
Thanks. All right. Well, we can use this recursive definition to code a height function. As follows. We don't know which subtree is higher until we calculate the height. So let's calculate the height of the left subtree and save that, and let's calculate the height of the right subtree and save that. And now it's just, you know, if left is bigger than right, then left is the highest tree. Let's just return left plus 1. Otherwise, let's just return right plus 1. And be a little careful with your if-elses. So it may be tempting to say if left is bigger than right, return left plus 1. If right is bigger than left, return right plus 1. And that doesn't handle the case where left and right might be equal. And I may just fall off the bottom of my function and not tell it what to return, and it might return some, you know, random ridiculous number. But this is nice and safe, right? If left is bigger than right, return left plus 1. Left subtree is highest. Otherwise, return right plus 1. Right is highest or same as left. Or I could have done, you know, if left is bigger than or equal to right, return left plus 1. And then this would only happen if the right was bigger, right? But work through all those different possibilities, it ends up being exactly the same thing. And we're still a little new on recursion, but what's the one thing that's missing up here in this nice empty space at the top? What's the one thing we always...
It's null or something? Or
Yeah, we gotta have a base case, right? Something to go along with a base case in induction. We gotta have some way to make sure we don't just keep calling height recursively on subtrees. Because, you know, if I try to find the height of this left subtree, first thing I'm going to do is try to find the height of this left subtree. And first thing I'll do is try to find the height of this thing's left subtree, which is null. And if I call height with a null root, this will segfault, because I can't dereference null. So we need a special checkup here which says if root is equal to null. And if root's null, we should return the height of a null tree. And here's the weird thing. Null trees have a height of -1. That's the thing that makes the whole thing work. That's the only time we actually return an actual number in our code. And why do null trees have a height of -1? Well, here's a tree with 2 nodes. What's the height of this tree?
One.
This is a height of 1. Exactly, because the deepest node is right here, and the number of hops from the root to that node is 1. So if I have a tree with just a root, what should the height of that be?
0 or -1.
Yeah, this is just a 0 because the deepest node is the root, and how many hops do we take from the root to the root? We don't have to take any hops. It's right there. And so a null tree, we kind of define that to be a height of -1. It should not have the same height as something with a root. And so we give it a -1, and it turns out if we do that, this works perfectly. And it's the idea that the left subtree should have a height 1 less than the height of the tree. Well, the left subtree is null, so its height has to be -1. So this is kind of the one statement that makes everything work, and the rest is just, you know, a recursive formula. All right, we are a little bit past time. So we'll do a quick review of this on Monday, and then we'll go on and we'll start talking about tree balancing, and we'll talk about why height is an interesting aspect of trees. So we'll start off from there on Wednesday. Come by office hours tomorrow if you want to talk about PA3 or if you have other questions. Otherwise, have a good one. I will see you next time.
Thank you. Bye-bye.